We left off last time discussing a wave model for sinusoidal traveling waves. We now transition from theory to reality by discussing an actual traveling wave created on a specific medium, a taut string. We'll also consider what happens when a wave travels from one medium into a different medium. Okay, whether a piece of string of different composition or even a fixed or movable boundary. We'll look briefly at the energy and power transmission at the boundary, okay, as well as for traveling waves in general. And finally, we'll look at the linear wave equation, which can be used to describe all traveling waves, whether mechanical or electromagnetic in nature.
So we left off last time introducing a special class of traveling waves called sinusoidal traveling waves. These waves can be represented as sine or cosine functions, which means that they are periodic, having a pattern that repeats in a regular interval of time. We'll now make this theoretical discussion a little more real by applying these waves to the specific case of strings. Strings are fairly important in the world of physics and the world of music, as many instruments create sound waves by getting strings to vibrate. So we start by asking the question, okay, how are these sinusoidal waves created on strings? Okay, well, as this simulation nicely shows, if one end of that string is attached to a simpler harmonic oscillator, and in this simulation, you see that this piston is simply moving in the vertical direction as a simple harmonic oscillator. Okay, it's moving in a transverse or perpendicular direction to the direction that the wave or the energy travels. So when one end of the string is attached to a simple harmonic oscillator, you will create a sinusoidal traveling wave in the medium. We want to talk about the transverse wave speed, okay, symbolized V sub y in the medium. Okay, what do we mean when we talk about the transverse wave speed? Okay, well, as this picture will illustrate here, okay, the transverse speed of a string element, okay, at a given position in the medium, a given position on the string, okay, represents, as I'm showing you here, if I look at this particular okay, little bead on our string here, this this bead at a specific position X, that bead simply moves up and down in the vertical direction, okay, as the wave propagates through the medium. So the transverse wave speed measures the speed of that particle at a specific position X at any time. Note that that particle oscillates up and down as a simple harmonic oscillator, and its speed changes continuously in time. It's important here that what we call V sub y, the transverse wave speed, is not to be confused with the speed V of the wave, okay, that we introduced in our last lecture. They measure two entirely different things. Okay, the wave speed V is a measure at which the wave propagates in the medium. Okay, it's a measure of how fast the energy travels in the medium. But remember, we said that a defining characteristic of waves is that while energy travels in the medium in the form of a wave, the actual particles in the medium, okay, do not have any net motion. Okay, so any particle in this medium, because it's a transverse wave, simply moves up and down in time. So the transverse wave speed V sub y is simply measuring the speed of any given particle in the medium at any time. So to come up with an expression for the transverse wave speed, we will start, okay, with our wave function that describes, okay, the traveling wave in the medium. Okay, our generalized wave function is a function of both x, the position of any particle in the medium, and time t. And if we take this function here, okay, Okay, y of xt shows you the vertical position y of the particle, any particle at position x at any given time. So by taking that and differentiating it with respect to time, note here we take the partial derivative, okay, of y with respect to time because it is a function of two variables, both x and time. So we're treating x as a constant. We're looking at the speed of a given particle in the medium, okay, a given tiny string element at any time. And when we differentiate, okay, our wave function with respect to time, okay, our sine function becomes a cosine function multiplied by, okay, the constant omega here. Note here that when we talk about the maximum value of that transverse wave speed, okay, well, when you look at our expression here, as we've said many times, a sine or cosine function has a maximum value of 1. So Vy max will be equal to omega times A being the amplitude, omega the angular frequency.
In the previous slide, we derived an expression for the transverse speed of a given particle at position x in the medium as a wave passes through the medium. Okay, we can similarly find the transverse acceleration of a given particle at position x in the medium, okay, by simply differentiating once more. That is, taking the partial derivative, okay, of our expression for the transverse particle speed. So here we have the expression that we derived in the previous slide for the transverse particle speed. Okay. If we want to find the transverse particle acceleration, we will simply differentiate the speed with respect to time. Okay, and just a note here, we're justified in taking partial derivatives as opposed to ordinary derivatives, okay, because we are finding the speed and acceleration for a given value of x. In other words, x is constant. The only variable is t. So you see here that by differentiating our expression for the transverse particle speed, which is expressed as a cosine function, by differentiating once more with respect to time, the cosine function becomes a sine function, of course, multiplied by the constant omega. So here we have it, our expression for the transverse acceleration of a particle. And since x is a constant, we said we're justified in taking, okay, partial derivatives as opposed to an ordinary derivative. And when we do so, we simply treat the variable x as a constant when we differentiate. So given our expression for the transverse particle acceleration, okay, we can find the maximum value of that, recognizing that the maximum value of the sine function is 1, okay, which tells us that the maximum acceleration of a particle, the transverse acceleration of a particle, okay, is going to be plus or minus omega squared times the amplitude. Right, so this is the problem that we looked at previously, where we were asked to write the wave function for a sinusoidal wave traveling on a string. We were given the frequency, the amplitude, the wavelength, and an initial condition which gave us the medium displacement y for a given position x at a given time, time 0. And from the three constants in the initial condition we were given, we were able to write the wave function for the wave, okay, as follows. So this is where we left off. Remember, this represents a sinusoidal traveling wave which is traveling to the left, okay, hence we have the kx plus omega t factor. Now, if we want to find the transverse speed of a particle in the medium, okay, we will take the partial derivative of the wave function with respect to time. Okay, remember that we are treating the position x as a constant here, which means that we must look at a given particle at a given position x when we evaluate this transverse particle speed. So differentiating, okay, with respect to time, okay, our sine function becomes a cosine function, and when we look at our argument of the sine function, the only term with time is the second term, 4 pi t. So when we differentiate, that brings us this factor 4 pi, okay, times 5 gives us the 20 pi, okay, cosine. In this problem, we're asked to find an expression for the speed of any particle in the string at any time, at a particular time of 2 seconds. So we will now substitute the value of 2 seconds in for time, okay, and when we do so, this is where we end up. This expression will allow us to find, okay, really the transverse particle speed of any particle, okay, at any position x, although we're not actually, asked to evaluate.
So in this slide, we are going to derive an expression for the speed of a wave, okay, that is traveling on a taut string. Now, I just want to point out here that in previous slides, we derived expressions for the transverse speed of a particle in the string, okay, which is very different from what we're doing here. Here we're talking about an expression for the wave speed, which is the speed at which the energy propagates in the medium, the speed at which the wave travels, which we said is distinctly different from the transverse speed of an element on the string. So to derive this expression, we are going to consider a wave pulse, a single pulse that is traveling to the right. And we're going to do something a little bit different here. We're going to analyze this wave pulse traveling to the right from the viewpoint of an inertial reference frame that is moving to the right at the speed of the wave, okay, such that the wave pulse appears to be stationary and all elements of the string move to the left, rise up, and follow the shape of the pulse. So remember that string elements in the reference frame at rest have no horizontal motion. So typically when we look at a wave that is traveling from a typical reference frame at rest, we say that the particles in the medium may move in a transverse direction, but they have no horizontal motion. This is one of the things that makes wave motion distinctly different from particle motion. The energy or wave travels horizontally, but the particles in the medium do not. So what that means is, from the point of view of our moving reference frame now, a reference frame that is moving, okay, along with the energy or the wave to the right, when we look at the motion of the particles now, rather than being at rest, these particles now move to the left with a speed opposite, okay, the wave speed v. So our particles now have motion to the left in this new reference frame. So we're going to consider a small element of string delta s, okay, as you see here in the diagram, a small element of string, okay, and when we look at this element of string here and we blow it up a little bit, this small string element we can think of as forming a piece of a larger circle. So it is an arc, okay, of a circle, and here you can see the center of the circle. So like we said, as the pulse moves to the right, okay, this little small segment of string moves to the left through this circular arc. So it therefore experiences a centripetal acceleration due to, okay, the tension forces that act on it. Now you see here in the diagram that the tension is caused here, okay, by the string. Okay, this string segment delta S is being pulled to the right, okay, with a tension force because of the string to the right, as well as it's being pulled backwards to the left because of the string that exists to the left of it. So the tension in the string is constant, so these two forces are equal in magnitude, although they have different directions. So when we consider the vector nature of these tension forces, we see here that same magnitude, the horizontal components of those tension forces will cancel, okay, but the vertical components do not. And notice that the vertical components of these tension forces act in the centripetal or radial direction towards the center of the circle. So these combined vertical components, okay, provide the centripetal force. So when we apply Newton's second law, okay, to the case of uniform circular motion here, we see that the centripetal force, that is the net radial force downwards, is equal to 2t times the sine of theta, which is equal to the mass times the centripetal acceleration, which we will write in terms of wave speed, since our goal here is to get an expression for the speed of a wave, okay, traveling down this string. So we will use this small angle approximation. Because this piece of string delta S is so small, these angles here, theta, are so small, we can approximate this saying that the sine of the angle theta is about equal to theta. And remember that for values of theta that are less than 10 degrees, okay, this small angle approximation has less than a 1% error in it. So it's a very good approximation. To represent the mass of the string, we will use the concept of string density. So the mass of this little segment of string is just equal to the string density mu, the mass per unit length, times the length of the string delta S. And delta S we will represent, remember we said it is a piece, an arc length of this larger circle. So that arc length is equal to, okay, twice theta times the radius, so 2 times r times theta. Making these substitutions, okay, into Newton's second law, okay, the left-hand side of Newton's second law, our expression for net force, 2t sine theta becomes 2t theta with our small angle approximation. M, okay, becomes mu times 2r theta, and we'll keep the v squared over r term there. Okay, you'll notice the r's cancel out on the right-hand side of the equation. This factor of 2 theta on the left will cancel with a 2 theta on the right. And when we solve this for v, we come up with the end result that v, the wave speed, okay, the speed at which the wave propagates on that string, the speed at which it moves horizontally, is equal to the square root of the tension in the string divided by the string density, the mass per unit length. So let's apply this newfound equation, okay, describing the speed of a wave in a string, okay, in the form of a specific example. So in this example, we're told that a 100-meter long wire has a mass of 130 grams. A sample of the wire is tested and found to break at a tension of 150 newtons. What is the maximum propagation speed for transverse waves on this wire? So note here that because the wave speed is directly proportional to the square root of tension, the maximum speed of the wave on that string, that wire, will occur for the maximum value of tension in the string. So using our equation for the wave speed in a string, okay, square root of tension over, okay, the string density, the mass per unit length, okay, like we said, the maximum speed occurs for the maximum tension of 150 newtons. We will plug in, we're given the information, 130 grams or 0.130 kilograms in MKS units divided by 100 meters gives us a measure of the string density. And when we do the number crunching, we come up with a speed of 340 meters per second, which, by the way, coincidentally is typically the speed of sound in air at room temperature. So in this example, we'll take a closer look at factors or actions taken that affect the speed of a traveling wave on a string. Now, some of these factors are obvious, some not so obvious, and some of the factors or actions we look at may seem like they should affect the wave speed, but in fact, do not, as we shall soon see. So in this example, we're told that a transverse pulse is created on a taut string by moving your hand up and down quickly a certain distance. Describe how each of the factors or actions will affect the wave speed. Will the wave speed increase, decrease, or stay the same? So we'll take a look at a simulation of this in the next slide, and hopefully this simulation will go through these actions and help us make sense of which will and will not affect the speed of a wave. So we see that for a wave traveling on a string, the wave speed is affected by the string tension as well as the mass per unit length, sometimes called the string density. While this is very specific to a wave traveling on a string, we can say in more general terms that the wave speed will be directly proportional to some sort of elastic factor. For the case of a wave on a string, that's measured by the tension, and inversely proportional to some inertial factor. In the case of the wave on the string, that was measured by the string density. In general, though, we can say that the wave speed is affected by the medium itself. That's it. So anything, any factor or action that would change the medium should affect the wave speed. But there are some other factors or actions that can be taken that may seem like they should affect the wave speed, but do not, because they do not change the medium in any way. Some of these factors deal with the creation of the wave in the first place. So as the chart will indicate here on the left, let's take a look in this simulation at taking certain actions and just visually or qualitatively looking at how it affects the wave speed. So the first action we'll take is, what about in creating the wave, we can move our hand slowly or quickly. So I'm going to manually create a wave here by moving this wrench. So in the first case, I'm going to move my hand up slowly. And if you look at, you can kind of visually see the wave speed. Let me now move my hand up about the same distance but more quickly. And you see that the speed of those two waves really is the same. Here's a slow movement. Here is a fast movement. Now clearly the slow movement creates a longer wavelength wave, than the fast movement. But the wave speed is pretty much the same in both cases. Likewise, when we create the wave, I can create the wave of a small amplitude, by moving my hand up a short distance, or I can create a wave of larger amplitude by moving my hand up a larger distance. Let's try that again. I'll try to change the magnitude. So here is a small amplitude wave. Take a look at its speed. Here's a large amplitude wave. And you can see that the amplitude clearly changes, but the speed of the wave does not. Now, if we want to change a factor of the medium, like the elastic property of the medium, by changing the tension, that will certainly affect the wave speed. So let's take a look here at a low tension wave, and I'm going to use the manual oscillator here. You can visually measure the wave speed here, and let me stop that here. Let's gradually increase the tension here and see what happens. You can see what happens to the wave speed here, as you increase the tension. So the tension clearly does affect the wave speed, because in that case we are affecting or changing the medium. There's no way with this simulation I can show you the third factor, which is to change the string density. Okay, so we'll just have to consider that in theory. Just to summarize or recap what we just illustrated in our simulation, so you can get this in your notes. So when your hand is moved more quickly up and down, but still moved by the same amount, okay, we say that this may decrease the wavelength, okay, it may even change the frequency, but it does have no effect on the wave speed. And similarly, if your hand moves more slowly up and down, okay, this will affect the wavelength, but not the wave speed. If your hand moves a greater distance up and down, this will affect the amplitude of the wave, causing a greater amplitude wave, but once again, no effect on the speed at which the energy propagates in the medium, the speed at which the wave travels. And likewise, hand moves a smaller distance, you create a smaller amplitude wave, but it has no effect on the speed. Now, we couldn't show in the simulation the effect of changing the string density, but as you know, the wave speed goes like the square root of the string tension divided by the string density. So if you use a heavier string with a greater string density, that inverse relationship tells us that the speed should decrease, right? So the wave speed is inversely proportional to this inertial factor, okay, which is measured by the string density. And conversely, if we were to use a lighter string with a smaller string density, that would cause the wave speed to increase. We did see in the simulation the effect of changing the tension of the string. So when you increase the tension, as our equation predicts, the wave speed should increase, as we saw. And likewise, when you decrease the tension, the wave speed will decrease.
We'll now introduce a new topic, that is the reflection and transmission of waves at boundaries between media. The principles introduced here will be needed when we begin our unit on optics at the end of the course, where we'll specifically talk about properties of electromagnetic waves. So we know that the speed of a wave depends upon the medium in which it travels. One of the factors that determines how fast a wave travels in a medium is the elasticity of the medium itself. Okay, for example, we previously said in today's lecture that for a wave traveling on a string, the tension in the string will affect the speed of the wave. Okay, the tension is a measure of the elasticity of that medium. So we'll discuss other elasticity factors when we talk about other types of waves, okay, in the near future. So when a wave traveling in a given medium enters a new, different medium, we would expect that the speed of the wave should change as well. Okay, if you take a look at the simulation, you will notice that as the wave traveling in medium 1 enters medium 2, okay, first of all, you'll notice that the wave slows down. As you'll find out later in the course, medium 2 has what we call a higher index of refraction, okay, which for electromagnetic waves means that they will travel slower when the index of refraction is higher. So you can clearly see just by visually looking at the simulation that the wave speed decreases as the wave enters the new medium. Okay, you should also notice here that in addition to the change in wave speed, you can see that the wavelength changes as well. Okay, so as a wave goes from one medium into another, the speed and wavelength change. Okay, but what can we say about the wave's energy? Okay, since that's what waves are really all about, they're means of transporting energy from one point in space to another. Okay, well, it turns out that when a traveling wave encounters a new medium, part of that energy gets transmitted to the new medium and part of it gets reflected back into the incident or original medium. Now, the simulation that we looked at previously, it nicely shows the change in wave speed, okay, as the wave enters the new medium, but it doesn't accurately depict the change in the wave amplitude that would result. Okay, so, if you want to ask the question in terms of wave properties, how can you determine how much energy gets transmitted or reflected at the boundary between the media? Okay, look at the amplitude of the wave, since the amplitude is a measure of the energy that the wave possesses. Okay, to see what happens at the boundary between the two media, we need to look at another simulation. Okay, so we'll take a look at the simulation here. And you'll notice that, okay, well, let's wait to start the simulation at the right time here. The wave pulse in the light string travels towards a heavy string, okay, where we would say it encounters a new medium. When the wave pulse reaches the boundary between the two media, okay, the boundary where the medium turns from, light string to heavy string, some of that energy gets transmitted, okay, into the new medium, but notice that some of that wave's energy gets reflected back into the incident medium. Okay, you can see in this simulation that the transmitted wave has a smaller amplitude than the incident wave. Okay, while of course the law of conservation of energy dictates that since energy is neither created nor destroyed, the total energy of that incident wave must be exactly equal to the sum total of the energy of the transmitted wave plus the reflected wave at the boundary. All right, so we said on the previous slide that we can determine how much energy gets reflected at the boundary or transmitted into the new medium, okay, by looking at the amplitude of the wave, since the amplitude is really a measure of the energy of the wave. Here we want to ask the question, what is it that determines the amount of energy that gets reflected versus transmitted? Okay, you could get a lot of energy transmitted, not much reflected, or vice versa. Remember, the conservation of energy is alive and well. So the total energy of the reflected and transmitted wave, okay, cannot be more than the total energy of the incident wave. Well, it turns out, what is it that determines how much of the wave energy will be reflected versus transmitted to the boundary? Okay, it's the difference in wave speed between the two media. When the media are very similar, okay, when the media, the initial medium and the transmitted medium are very similar, most of the energy gets transmitted, very little of it gets reflected. But when the media are very different, okay, for that case, most of the energy will get reflected, very little will get transmitted. So the key word here I've highlighted in pink is difference in wave speed between the two media.
So we said that the amount of energy reflected versus transmitted depends on the difference in wave speeds between the two media. But something else happens that may seem a bit surprising, and that is, in some cases you get a phase change upon reflection. So when we look at the wave that is reflected at the boundary between the two media, sometimes it will experience a phase change, and we'll describe exactly what we mean by that in a second. So to understand this, let's consider a wave that is traveling from medium A to medium B, okay, where we can say that the speed of the wave in medium A, okay, is greater than the speed in medium B. So said in a different way, here's an example, okay, where a wave traveling in the initial medium will slow down in entering the new medium. So as you see in this simulation here, we have a wave that is traveling from left to right. We're moving in a thin string to a thick string, and you would expect, from this relationship up here, that Okay, there's this inverse relationship between string density and speed. Okay, so for a constant tension, when the wave pulse hits the thicker string, it's going to slow down. Its speed is going to be less. So in this case, what happens to the wave pulse that is reflected at the boundary? Well, look at the simulation. Here's the reflected pulse right here. Do you notice that that pulse is now inverted? It starts, okay, moving down in the upward direction in our simulation, but when it gets reflected, okay, that pulse is now below the equilibrium line. It's in the downward direction. So what we mean by an inverted pulse. This is generally true whenever a wave, okay, travels into a new medium, okay, where it travels slower. That reflected pulse will be inverted. Likewise, when we have the opposite situation, when we have a wave that is traveling from, let's say, a thicker string to a thinner string, okay, in this case, the wave speeds up in the new medium. Notice what happens to the reflected pulse. Okay, the incident pulse is up, and the reflected pulse here, you'll notice, is also up. So in this case, there is no phase change. We can say that that reflected pulse is erect. Okay, there's no phase inversion or phase change. Now, what you should note here is, in addition to the reflected wave, there is a transmitted wave. Notice that in both cases, the transmitted wave experiences no phase change. Okay, so an upward pulse traveling to the right, that transmitted pulse is upwards. We have an upward pulse traveling to the right in the bottom picture, the transmitted pulse is upwards. No phase change, okay, is ever experienced for the transmitted pulse. So in the previous slide, we gave a set of criteria for determining when a wave that is traveling from one medium into another will experience a phase change upon reflection at the boundary. And we gave this criteria, we expressed it in terms of the wave speeds. So in this problem, and very often in other problems, you will be given information not about the speed directly, but information from which you will have to then take the added step of figuring out the wave speed from the information given. So for a one-dimensional wave traveling on a string, we know the wave speed is directly proportional to the square root of string tension divided by the linear string density. And we're told in this property that, we've mentioned this before, that in general, the speed of a wave in any media, whether it's a string or let's say a sound wave traveling in 3 dimensions, the speed will go like the square root of an elastic property of the medium divided by an inertial property of the medium. So in this particular problem, we're asked to make a determination on whether there's going to be a phase change upon reflection for a wave that is traveling from medium A into medium B. Okay, first, when the tension changes. So we have a wave traveling on a string. When the tension of medium A is greater than the tension of medium B, is there going to be a phase change upon reflection? Well, we have to take this added step of saying, well, how does a tension relate to the wave speed? We know that the wave speed is directly proportional to string tension. So greater tension in medium A means greater speed in medium A, in which case here's a case where the wave slows down, okay, as it enters the new medium. In that case, we know that when a wave slows down upon entering the new medium, the reflected pulse will be inverted. Okay, we'll experience a phase change at the boundary between the media. Likewise, if we do the opposite, if it looks like the tension A is less than in B, okay, so that the wave will speed up upon entering the new medium, in that case there will be no phase change upon reflection. In the last 2 parts of this question here, we're asked to make a comment on density. Well, from our expression, we know that the wave speed is inversely proportional to the string density. So if the density of medium A is greater than the density of medium B, okay, then that means that okay, the speed of medium A should be less than the speed in medium B. So here's a case where the wave should speed up as it enters the new medium, in which case there will be no phase change at the boundary for the reflected pulse. Okay, that reflected pulse will be erect. And when the converse is true, conversely, when the density of A is less than the density of B, here's a case where the wave will slow down upon entering the new medium, because of that inverse relationship, in which case there will be a phase change upon reflection.
We're now going to briefly discuss the rate at which energy gets transferred when sinusoidal waves travel down strings. Okay, what we're really talking about here is a measure of wave power. Power, you recall, is a measure of the rate at which energy is transferred across the medium, the rate at which energy travels in the medium. Now, the expression for the wave power along a taut string is quite a complex derivation. And we're going to postpone the derivation until our next unit, where we will, in great detail, derive the expression for the power transported by a longitudinal wave. The expression for the power of a longitudinal wave is virtually the same expression we get for a transverse wave. So we're going to simply state the result right here. There's really no reason to derive this expression twice. Okay, and I know how disappointed you must be feeling right now, and I'm sorry. Patience, remember, is a virtue, and very often good things happen in life to those who wait. So we'll postpone the derivation. You're not going to get cheated out of it. Like I said, we'll do the derivation, for the power of a different type of wave. It's pretty much the same physics. Rather than a wave traveling on a taut string that is transverse, we'll look at a wave that is transported, as a longitudinal wave in a medium. But for the wave on the string, here's the expression for power. It turns out that, after the derivation, the power of that wave, the rate at which the energy gets transferred along the taut string, goes like 1/2 the linear string density mu times the square of the angular frequency omega times the square of the amplitude of the wave times the wave speed to the first power. So what we want to do, if we're not going to derive this relationship, we at least want to understand it. And so we're going to take a look at the simulation in the next slide, where we'll try to make sense of these relationships. And in particular, we're going to look at the relationship between the power of the wave and wave amplitude, between the power of the wave and the wave speed, and between the power of the wave and the wave frequency. And then after watching the simulation on the next slide, you can come back and fill in your notes here, and hopefully, it will make a little bit more sense once you visualize what's going on.
So in this simulation, we'll take a look at some of the factors that affect wave power. Remember that the power of a wave is a measure of the rate at which energy is transferred across the medium, the rate at which energy travels in the medium. So really, there's two factors that should affect the power of a wave, when we look at the definition of power, as a measure of the amount of energy, per unit time. So certainly the amount of energy that the wave carries will be one of the factors that affects the power of the wave. And the second factor will be the amount of time it takes for that energy to get transferred, along the medium. So we're going to take a look at three factors here, of course related to the energy and time factor that will affect the power of the wave. So the first factor we're going to take a look at is wave speed. And In this simulation, we can control the wave speed by controlling the tension in the wave. So we're going to start out by taking a look at a wave that has a low tension and therefore a low wave speed. To visually measure the power, I'm just going to stick this ruler at a certain point in the medium. And if we focus our attention on the left-hand side of that ruler, we can see the rate at which energy is crossing that boundary line. So you can see here for a low tension wave, okay, the wave has a certain speed. There's a certain amount of energy crossing the left-hand side of the ruler per unit time. Let's take a look at what happens as we increase the tension. Okay, you can see here as we increase the tension, clearly the wave speed increases, okay, and more energy is crossing that ruler per unit time. So that is one of the factors. Let's take a look at a second factor, which is the amplitude of the wave itself. So in this case here, we will start by looking at a small amplitude wave. Okay, and remember that the amplitude of a wave is a direct measure of the energy. In order to create a wave of a large amplitude, a lot of energy must be added to the medium. So in this simulation, energy is added to the medium in the form of this vibrating piston. If this piston moves up and down a short distance, like it is now, it creates a small amplitude wave. And you can see the amount of energy that is crossing the left-hand side of the ruler. Let's increase the amplitude of the wave, making that piston move a greater distance. Okay, and you can see what happens that, okay, a lot more energy, okay, is crossing that boundary, okay, in a given interval of time. Okay, so as the displacement of the medium increases, the amplitude of the wave increases, so does the energy and the power. Okay, the other factor we will take a look at is the wave frequency. Okay, remember the wave frequency measures how many waves per unit time are passing a given point in the medium. So let's start by looking at a low frequency wave. Okay. So in this case here, we see that for a low frequency wave, okay, you can visually measure, okay, qualitatively measure, how much energy is crossing that left-hand side of the ruler in a given time interval. Okay, let's now increase the frequency here, and you will see what happens. Okay, as we increase the frequency, okay, you can see that a lot more energy per unit time is crossing that boundary. So all of these factors we look at, okay, are directly proportional to the power of the wave. So the last topic that we will introduce in this video is the linear wave equation. Now, we're not going to spend the time to derive this. We can't derive everything, okay, but I do want you to realize that this linear wave equation results from applying Newton's second law to a mechanical wave traveling in the medium. So when you apply Newton's second law to the mechanical wave traveling in the medium, you will come up with this second order linear partial differential equation, which is the linear wave equation. Very important in physics. Okay, it not only applies to any traveling wave, okay, of this form, okay, where the wave is a function of x plus or minus the wave speed times the time, okay, but it applies to both mechanical waves and electromagnetic waves. So believe it or not, okay, when you take Physics 103 and we talk about the all-important Maxwell's equations for describing all electromagnetic phenomenon, that we will use this equation, the linear wave equation, in our derivation of two of Maxwell's equations for electromagnetic radiation.
Even though we're not going to derive the linear wave equation, we are going to use it to prove that a sinusoidal traveling wave satisfies the linear wave equation. So let's start out. Here is our generalized wave function, okay, for any sinusoidal traveling wave, okay, whether it's traveling to the right or to the left. Remember, we said we could express it in terms of these constants: A for amplitude, K for wave number, omega for angular frequency, and phi a phase constant. Notice that this generalized wave function is a function of both position x and time t. Okay, here is our linear wave equation. So in order to use a linear wave equation, okay, we are going to need to differentiate our wave function with respect to both x and time. Okay, so let's start out here. We're going to take the partial derivative of our wave function with respect to x. That turns our sine function into a cosine function. And remember, when you take the partial derivative of the function with respect to a variable, okay, in this case x, we will treat any other variable, okay, in this case t, as a constant. So when we differentiate the sine function with respect to x, okay, we have to multiply by the factor k, but we treat t as if it were a constant in this case. We will differentiate our wave function once again with respect to x to get the second derivative. That will turn our cosine function to a negative sine function, once again multiplied by the factor k once again. Okay, let's now turn our attention to the variable time. So we'll differentiate the wave function with respect to time. Okay, again, that turns our sine function into a cosine function multiplied by the constant in front of time, which is omega. We'll again differentiate a second time to get the partial second derivative. That turns our cosine function into a negative sine function multiplied by this constant omega again. So we're now ready to plug into our linear wave equation. Okay, so let's plug what we have here into the equation. That is partial squared y partial x squared, okay, which we plug into the left-hand side, and partial squared y partial t squared we plug into the right-hand side. Okay, and not forgetting about this factor of 1 over v squared on the right-hand side. Of course, you'll notice here that there is a common factor, a sine kx plus or minus omega t plus phi, on both sides. Okay, we can, in simplifying, cancel that out from both sides, and the end result is we see that, yes indeed, okay, this wave function describing a sinusoidal traveling wave does satisfy the linear wave equation when we see that, okay, v squared equals omega squared over k squared, or v is equal to omega over k. And this right here, v equals omega over k, is nothing more than the wave equation, right? That is v equals lambda f, simply expressed in terms of these different variables. So we see here that, okay, the wave function that we've been talking about is indeed a solution, okay, to the linear wave equation.